So this is the second part of the talk. So this is me. So let's jump straight. So what I want to do in this second part of the talk is to actually talk about foundations, because during the first part of the talk, I didn't really talk at all about foundations. I just gave you some motivations and definitions. But with these motivations and definitions in place, we are ready to talk about the first important property of graph neural networks, which is that of permutation equivariance. Actually, let's begin by talking about the permutation equivariance of graph filters. So for your reference here, that's the definition of a permutation matrix. But what it's important here is that when you multiply by a permutation matrix, you reorder the entries of a vector. If you sandwich a matrix between two permutation matrices, you are doing a consistent reordering of the rows and columns of S. In the context of graph signals, this is important because it tells you if you're given a signal Sx and a graph signal in which you are perturbing both the shift operator and the signal X, that's just a relabeling of your signal. It's the same signal, just with different names on the nodes. Why is that important? Well, because if you have a graph signal X that is supported on S, and I give you a signal X hat, P transpose X supported on S hat, which is P transpose SP, all I have done is change the names of the nodes, right? So the processing of that signal should not change. So processing should be label independent. And what permutation equivariance of graph filters and GNNs tells you is that indeed this holds for graph filters and GNNs. Now, in order to be more specific, this is the problem that I am trying to study. So a graph filter is a polynomial on the shift operator S with coefficients hk. The outputs are given by this expression. This is what I have called a graph convolutional filter. If I consider running the same filter on Sx and on permuted or relabeled S hat, X hat, what I mean is the following, right? So I'm gonna have the blue filter where I am running coefficients hk on S, and the green filter where I am running coefficients hk on S hat and applying them to X hat, right? So the coefficients are the same, but the input is permuted and the shift operator is permuted as well. Now, if you do that, it takes one line to prove the following theorem, which you could call the permutation equivariance of graph filters, okay? Which says that if you consider consistent permutations of the shift operator and the signal, then the outputs of the filter are shifted versions of the output that you would observe in the unpermuted shift operator. The proof of that is this one-liner, by the way, so I don't want to make it sound like this is complicated. But what this means is something quite interesting. It tells you that graph filters are equivariant to permutations, which means that if you permute the input and the shift, you will be permuting the output. But of course, right, I mean, you ask the question whether this is a property that graph neural networks will have or not. The answer to that is yes, but just to be specific, the definition of the graph neural network is here, right? So we have filters that we apply at each layer, and these filters are composed with a pointwise nonlinearity. So the output of the GNN is the output of layer L. We are running now the same GNN on the shift operator S and the shift operator S hat, and we applied to signal X and signal X hat. I mean, that it is the same GNN means that at all layers, we are using the same set of filter coefficients. Okay? So one of the GNNs utilizes the shift S, is applied to signal X, utilizes filter H at each layer. The green GNN applies to signal X hat, runs on filter S hat, utilizes the filter tensor H, which is a collection of all the filters of all layers. So again, it's the same tensor, but a permuted input and a permuted shift. In that case, is another one-liner to show that GNNs are also permutation equivariant. So it tells you the reason why this holds is because the nonlinearity is pointwise, right? So in a sense, the nonlinearity is oblivious to the existence of the graph. There's nothing the graph can do, or let me rephrase that. I mean, there's no change in the graph that may lead to a different outcome in the operation of the graph neural network. Therefore, the GNN is also equivariant, which means that if you permute the input and the shift, right? So you permute the input and the shift operator, you will be also permuting the outputs of the graph neural network. Now, this tells you that your requirement to have signal processing or information processing that is independent of labeling is satisfied by the GNN. Okay, what I mean by that is the following. If I have this signal here supported on graph S, I consider a permuted version of that signal and a permuted version of the graph shift operator. This is the same figure that I showed you a couple of slides ago. If I now consider a processing of a signal on the graph on the left, there's some sort of diffusion is what I'm trying to signify with this graph. What the equivariance theorem tells me is that the output of the GNN will be a permutation of this output. But this is also the requirement that you had, right? So this is the sort of problems that I like to call lipstick on a pig. So one of these two red signals here on the left, you can call it lipstick, pig. The other one, you call it lipstick. Wow. One of them, you call it a pig. The other one, you call it a pig with lipstick. What's the one with a pig? Well, the one in which you relabel because you want to be permutation equivariant. The pig with lipstick is the one that your theorem claims that indeed you have achieved processing that is independent of labeling. In any event, what the permutation equivariance theorem tells you is that you are attaining processing that is independent of labeling. Now, that would be interesting in itself, but there is something much more interesting about permutation equivariance, which is that permutation equivariance is the key property that graph neural networks have that allow them to exploit signal symmetries. Now, what do I mean by symmetry? By symmetry, I mean the following. I mean, some graphs are such that they can be permuted onto themselves. Like, for example, in this figure, right? I mean, this graph is a regular graph. You can sort of put a mirror in here and reflect it. So that's what I've done to construct the graph on the right. But what matters is that it is possible for me to write the graph S itself as a permutation of the graph S. Okay, so the graph can be permuted onto itself. Now, the equivariance theorem applies in this particular case, right? So, but what it would mean is that if I do a permutation of the signal X and I run it on S, well, that's the same as doing a permutation of X and running it on P transpose SP because the graphs are, because the graph is symmetrical. It has this internal symmetry to it. But according to the permutation equivariance theorem, I know that this permuted processing here is equivalent to the permutation of the processing. Why is this important? Well, this is important because it tells you that you have learned to process this signal without ever having seen it, right? So a good intuitive example would be to think of this as a recommendation system. And you can think that in this recommendation system, you're trying to fill out the ratings of agent number 3, right? So this could be me, and this could be my group of friends. This one here is Rene and his group of friends, okay? So you have never seen Rene's friends, but nevertheless, because of the permutation equivariance of the GNN, you have learned to process Rene's friends from having seen how I am processing my own friends. Okay, now that's what I consider to be one of the critical observations for the practical importance of graph neural networks, that they are allowing you the possibility of leveraging internal signal symmetries. It's like you're multiplying the size of your data set, because just because you are seeing how my friends behave in this recommendation system, you will learn how Rene's friends behave without ever seeing them. And all that requires really is that the graph is permutable into itself. Now, this question of symmetries does lead to something that has to be remarked, which is that symmetry is very rare, right? So this cartoon picture that I am showing here in slide 10 doesn't really exist in reality. What does exist in reality is quasi-symmetry. So you have, a graph that can be sort of permuted into itself. Therefore, the question here that is important is not equivariance in itself, but stability to deformations, right? This graph cannot be permuted into itself, but it can be permuted into something that is close to itself. Do we have that sort of stability, which will give us a claim on approximate or close to equivariance? So the answer to that question would be yes, and this is what I will be trying to describe in the remainder of this talk. Formally, what I mean is the following. I want to be able to compare operators modulo permutation. And the question that I want to ask is what happens when the distance modulo permutation between my shift operators is small. Let me rephrase that. So what equivariance to permutations of graph filter tells you is that if the distance between your shift operators modulo permutation is 0, meaning if you have perfect symmetry, then the distance between your graph filters modulo permutation is also 0. The equivariance of GNNs tells you that if the distance modulo permutation of your shift operators is 0, the distance between your GNNs modulo permutation is also 0. What we want to prove is that if this distance is small, then these two distances are also small. What we will prove concretely is that this is not necessarily true, but that this is true. So that's the 1 minute summary of the next 40 minutes of this conversation. Now, before I move on to studying the stability properties of graph neural networks, let me introduce filter classes, because you can foresee that filters and GNNs are not going to be stable for arbitrary filters. You likely need to restrict the filters to which you are going to pay attention to. I will introduce, therefore, two classes of filters here. One of them is the class of Lipschitz filters. The other one is the class of integral Lipschitz filters. Before I introduce those, a reminder, right? So graph filters are polynomials on the shift operator S. They're given as I am showing here. So we have different coefficients. The S is the variable of the polynomial. The frequencies response is the same polynomial, but on a scalar variable, right? This is a polynomial in which the shift operator disappears. And we saw that knowing this frequency response is enough for us to be able to characterize these frequency response, these graph filters when they execute on a particular shift. The frequency response, however, the very important property that it has is that it is independent of the shift operator. Okay, so when we define filters that are of a particular class, we are defining them irrespectively of the shift operator on which they are applied. The first idea that comes to mind, I would guess, is that of defining a filter that is Lipschitz, in the sense that if the difference between the frequencies is λ2 minus λ1, the value of the filter is bounded by C. By the way, since our filters are analytic functions, they are in particular differentiable, and this condition here is equivalent to having the derivative of the filter's response being less than a certain quantity C. Now, a filter that is Lipschitz is not difficult to construct, so this is an example. An example is somewhat uninformative because it doesn't really tell you anything. The difficult thing is not to construct a filter that is Lipschitz. The difficult problem is to construct a filter that is not Lipschitz, because a filter that is not Lipschitz will need an infinite derivative at some point, okay? But anyway, so what matters here is whether the Lipschitz constant is small or large, right? So if the Lipschitz constant is small, then you have a filter that is not very discriminative because there's a lot of frequencies that this filter is letting pass. If the filter is, if the Lipschitz constant is large, then you have a filter that is more discriminative because the number of frequencies that you're letting pass has been reduced. Okay, so that basically is the trade-off that arises in Lipschitz filters, which is that the larger C is, the more discriminative that your filters become. Another class, which will sound strange, but will become important once we start studying stability properties, is that of integral Lipschitz filters, in which the condition is similar to what it was before, but I am going to divide by lambda in the denominator here. Okay, so instead of requiring the filter's response to be bounded by C times λ2 minus λ1, I am going to require the filter's response to be bounded by this quantity, And you can think of this quantity intuitively as saying that you want it to be Lipschitz, but with a Lipschitz constant that is proportional to the interval, to the middle point of the interval that includes lambda1 and lambda2. A more intuitive definition of the integral Lipschitz condition is here, since our filters are differentiable. You can see that this condition implies that lambda times h prime of lambda has to be bounded by C. Now that tells you quite a lot about the behavior of integral Lipschitz filters, because it tells you that at middle frequencies, nothing really changes. It's conceptually similar to a Lipschitz filters. But at low frequencies, they can be very thin because the derivative is multiplied by lambda, right? So if lambda is close to 0, h prime of lambda can be very large. At high frequencies, however, they have to be flat. So you cannot have an integral Lipschitz filters that has discriminability at high frequencies. So this will be perhaps one of the key insights of the talks. So please make a note to remember this for forthcoming discussions. So we are requiring the filter here to be flat at high frequencies. So it is impossible for the filter to discriminate features that live in high frequencies. Now, with these preliminary definitions in place, not with these preliminary definitions, I have discussed permutation equivariance, I discussed Lipschitz filters and integral Lipschitz filters. Lipschitz filters and integral Lipschitz filters are a preliminary discussion from what I'm going to do now, which is to study additive perturbations of graph filters. Now, to study an additive perturbation of a graph filter, let me show you a slide that is similar to the one that I showed you when I described equivariance, okay? But it's a little different, however. In this slide, what I'm trying to highlight is that I am going to be running the same filter coefficients on the same input signal, but on perturb shifts. What changes between the blue and the green is that in the blue, I am using shift operator S. In the green, I'm using shift operator S hat, but the filter coefficients and the input signals, they are the same. Now, I want to study perturbations. So something that would be reasonable to do here, right, is to add an error matrix to S that would give me S hat. So for any E that I choose here, this will be the difference between the two shift operators. Therefore, the norm of E quantifies their difference. But this has a flaw, of course, right? Which is that we know that the graphs S and S hat, when they are permuted versions of each other, they are the same. That's just a relabeling. Yet we would not have E equals 0. But we already introduced a solution to that problem, which is to utilize operator distances modulo permutation. I could leave it at that, except that I need to have a handle on the error matrix. Therefore, I am going to walk you through this slide, which contains a number of definitions. I am defining here all of the matrices E tilde that allow me to write permutations of S hat as summations of S and E tilde. So for each permutation P, I have a different E tilde matrix measuring the error. And of course, the error matrix modulo permutation is the one with the smallest norm, right? So I am comparing S to the permutation of S hat that makes it closest to S. That's what this distance D of SS hat is measuring, and it's nothing but the norm of E. And this is not a new definition relative to the operator distance modulo permutation. It's just a different way of writing the operator distance modulo permutation, but one that gives me a specific handle on the matrix E that measures the distance between these two operators. Now, the reason why I want this handle is because I want to be able to compare the eigenvectors of the shift operator S with the eigenvectors of the error matrix E. And that will be given by this constant delta, which is the difference between the eigenvectors of U and the eigenvectors of V plus 1 squared minus 1. You don't have to remember the specific form of this constant delta, just that it relates U and V. It measures how different U and V are. The other important aspect to notice of U and of delta is that U and V are unitary matrices. Therefore, delta is at most 8. Okay, it's never a large number. It can be small if these eigenvectors are close. And that's the reason why we define it, because we know that in some perturbation models, U and V are going to be close to each other. But if we don't know that they are close to each other, we can just replace delta by 8 in the bounds that I am going to introduce in the next few slides. Now, and speaking of these bounds, so this is the first theorem that I would like to introduce. It says the following. We have a filter H and shift operators S and S hat. The shift operators, they contain n nodes. The following three hypotheses are assumed here. The first one is that the shift operators S and S hat are related by this perturbation model, which is the one I have introduced. Hypothesis number 2 tells you that the error matrix E has norm epsilon and that the eigenvector misalignment constant is delta. This measured relative to S. And hypothesis number 3 tells you that the filter is Lipschitz with constant C. If this hypothesis hold, then the distance modulo permutation of the filter differences is bounded by C times 1 plus delta square root of n times epsilon plus terms that are of order epsilon square. Now that's a stability bound for the outputs of graph filters. It tells you that if the perturbation of the input is small, the perturbation of the output is also small. And all of these things are measured modulo permutation. You know, perhaps it is important that I parse this bound for you. So I am repeating the bound here. As I was telling you, right, if S and S hat are epsilon close, the filters are also epsilon close, and this is modulo permutation, which is important because it allows us to consider internal signal symmetries. The other important point here is that the bound is proportional to the Lipschitz constant of the filter's frequency response C. Not integral Lipschitz, by the way, Lipschitz constant of the filter frequency response. And it is also proportional to 1 plus delta square root of n. This means the bound is not great for large graphs, okay? Unless you know that one way or another, your misalignment decreases with n, which is true in some statistical models of graphs. But anyways, if you don't have that, the growth with n can be at most 1 plus 8 square root of n, because delta cannot be more than 8, and you know that's not good, but it's not that bad either. There are some remarks that I think are worth making here. The first one is that we are Lipschitz continuous with respect to the perturbation size epsilon with this particular Lipschitz constant. So this is stronger than claiming continuity, which would simply say that outputs are small if input changes are small. So that's why we talk of stability, not continuity, because well, that's what this bound means. The second important aspect to remark here, perhaps more important than the first, is that the bound is universal for all graphs of a given size. There is no parameter here that depends on the graph. Doesn't depend on spectral gaps, doesn't depend on any spectral property of the graph, doesn't depend on degree, values, etc., etc. There's nothing here that depends on the graph. There's a property of the filters, C. There's a property of the error matrix, delta. There's a property of the graph, of course, that's n. That's why I say that the bound is universal for when the number of nodes is given. And there's another property of the perturbation, which is the size of the perturbation. Okay, so we have something that depends on the filter, two quantities, delta and epsilon, that depend on the perturbation matrix, but nothing here is dependent on the graph. The other important aspect to remark here is that the filter's Lipschitz constant C, that's a controllable design parameter, or actually controllable learnable parameter, if you wish. These filters are not chosen. These filters are going to be learned, okay? But if we desire more stability, we can take measures during our training to make the constant C smaller. Of course, this constant C will play a role in the discriminability stability trade-off. I'm going to be talking about that a second into the future. But before I talk about that, let me tell you about the other part of the bound, which is this 1 plus delta square root of n, which does not really depend on anything that is under the control of the system designer, right? So perturbations are what they are. So this delta constant is what they are. The size of the graph that you are studying is what they are. So there's no control that you have on the number of nodes of the graph. Therefore, there's nothing you can do as a system designers to affect this second part of the graph. Now, regarding that stability trade-off, right? So, stability to additive perturbations. Yes.
I had a question. Could you go back to the previous slide? So, has there been any work where the training of the network is done in a way that you control the Lipschitz constant so that you can ensure that trained networks satisfy this property?
So the answer to your question is yes and no. In the paper where we prove this theorem, we performed that experiment to show that indeed, if you force the constant C to be smaller, your outputs are more stable. But there hasn't been a paper where this is explored in detail.
But how hard would it be to impose? How hard would it be to impose Lipschitz continuity constraints during training?
That's a great question. It's not that difficult, Rene, because the Lipschitz condition depends only on the coefficients of the filter. It doesn't depend on the graph. So it's like adding a regularization for the, actually literally adding a regularization on your filter coefficients.
Great, thank you.
Yes. So the Lipschitz constant C, right? So remember, is like a bound on the derivative of the filter, but the filter is a polynomial. Therefore, the derivative is also a polynomial. So you just need to require that polynomial to be bounded for a range of lambdas. Yeah, it's not difficult to impose.
Yeah. My other question was going to be whether there are ways of exploiting the graph of the structure of the graph. For example, maybe that there is a bounded degree to reduce the square root of n to something smaller.
Right. Correct. So your other question here is what can we do by looking at the specifics of the graph? I think that there is a lot to be done here. So you can look at imposing conditions on the graph. You can look at statistical models of graphs. That would be graphs that you sample from graphons or graphs that you sample from manifolds. I've worked on graphons, and Gita has very interesting work on sampling from manifolds. So there's quite a lot to be done here in terms of studying models of perturbation that are richer, or actually poorer perhaps, but anyway, so stricter than the ones that we are considering here. So you can see here that we are not imposing any condition on the graph, and we are not imposing any condition on the perturbation. It is, of course, a very interesting and at the same time very open research topic to study other forms of perturbations that would lead to better bounds that shed more light on the behavior of the GNN. Any other question, Rene?
No, thank you.
Okay. Okay, so let's. By the way, right? I'm not still talking about GNNs. I'm still talking about graph filters. An important, very important property here is that I am restricting the filters to be Lipschitz, and Lipschitz filters are good news because they offer a genuine stability versus discriminability trade-off. You want your filters to be more discriminative, you make them thinner. In making your filters thinner, you are going to be increasing your Lipschitz constant. But anyway, so you have this trade-off, and this trade-off holds regardless of frequency. So if you tolerate enough, if you tolerate enough instability, should say here, so sorry about this typo. If you tolerate enough instability, you can always discriminate your features. Now, but these additive perturbations that I was just describing, they give good results, but the good results that they give, they're a little bit of a mirage, because additive perturbations really are not meaningful. Okay, so here I'm trying to illustrate why this is not the case. So you have a graph here in which you have a strong community on the left, a weak community on the right, and you add this perturbation in which all of the weights are 1. You know, if little w is much smaller than 1, which is much smaller than big W, is this a large perturbation or a small perturbation? Well, I mean, it's difficult to tell, right? So, because intuitively speaking, the perturbation is large because you're changing the graph drastically. This community here now is strongly, somewhat connected, whereas before it was barely connected. However, if you compare the norm of S to the norm of E, the norm of S is much larger than the norm of E. Right? So therefore, if you compare the norm of the perturbation, you would think that the perturbation is small, but intuitively the perturbation is not small. What you need actually is to tie the perturbation to the structure of the graph. And tying the perturbation to the structure of the graph calls for the use of relative perturbations. Right? So for example, here I am perturbing this big community by epsilon W and this weak community with epsilon little w. So if you ask me whether this perturbation is small or large, yes, indeed, it's a small perturbation. I mean, the graph is not changing much. Right? So edges with small weights change a little, edges with larger weights change more. Now, with this motivation, I introduced this relative perturbation model where the signal S hat is perturbed to S plus ES plus SE. So the reason for the double product here is to be able to have symmetric permutations. Not to be able to, I mean to restrict the perturbations to be symmetric. As we did before, we can define this set of relative error perturbation matrices, right? So I am considering here all possible permutations of the graph S hat. And the relative error matrix modulo permutation is the one in this set which has the smallest norm. Therefore, what I'm searching for here is the following. I am looking for the permutation of S hat that makes S hat as close as possible to S. The error matrix E that allows me to write S hat in this form is the one that I'm going to call the relative error perturbation. And again, the norm of E is a measure of how different these two matrices are. And this allows me to introduce this alternative theorem, which looks a lot like the one that we had before, right? It says that if hypothesis number 1, S and S hat are related by this expression, which is now not an additive perturbation model, but a relative perturbation model. The error matrix E still has norm epsilon and still has eigenvector misalignment constant delta. That's again measured with respect to S. But the filters now are required to be integral Lipschitz with constancy. With these assumptions, this bound can be established, which is very similar to the bound we had before, except that now we have a 2 multiplying the bound, but other than that, it reads identical. Now, the bounds are misleadingly simple, right? Because there's 2 significant changes in the hypothesis. I mean, the bound looks about the same, but the perturbation now is not absolute. The perturbation is relative. And the filter is now not Lipschitz, it's integral Lipschitz. So the constant C here, I am using the same letter, so it makes the bound looks identical, but the C for Lipschitz and the C for integral Lipschitz, they're very different quantities, right? So in that sense, the bound is very different. Of course, I've written here it with the intention of highlighting the similarities. Now, the similarities tells you that the parsing of the bound is analogous, right? So if the S and S hat are epsilon close, the outputs are epsilon close, except that now epsilon closeness is relative, it's not absolute. The bound now is proportional to the integral Lipschitz constant, it's not proportional to the Lipschitz constant. And it is still proportional to 1 plus delta square root of n, so that part of the bound remains unchanged. Again, stability is stronger to continuity, right? But except that now the Lipschitz continuity is with respect to a relative perturbation term. The bound is still universal. It depends on properties of the filter and properties of the perturbation, but it doesn't depend on properties of the graph except for the square root of n. And the eigenvector misalignment, as before, is a quantity that is outside the control of the system's designer. But what is under control of the system's designer is the integral Lipschitz constant C. Now, as before, right, this integral Lipschitz constant C controls stability. So the smaller it is, the more stable the filter is. The higher it is, the less stable the filter is. But it also controls discriminability. Alas, however, it is not as good news as was the case of Lipschitz filters, because we have seen that integral Lipschitz filters, they do not offer a genuine stability discriminability trade-off. What do I mean by that? Well, what I mean is that if you look at high frequency features of your signal, it is always impossible for you to discriminate them with an integral Lipschitz filter. There are caveats to this expression, okay? I am using language loosely, so maybe I should be less loose and more precise about it. What I mean by this is the following. So the constant C, of course, it affects discriminability as before, right? So you can increase C to improve your discriminability. However, it will always be the case that when your frequencies are sufficiently large, you lose the discriminability no matter how large C is. If you give me a filter that is integral Lipschitz with whatever constant C you want, it could be very high. It is possible for me to move up sufficiently into the frequency domain and force you into losing the discriminability of your integral Lipschitz filter. If you want me to be even more precise than that, what is very significant about relative perturbations is the fact that the use of integral Lipschitz filters gives us a stability constant for which the discriminability properties are different at different frequencies. In the case of additive perturbations and Lipschitz filters, the stability versus discriminability trade-off is the same for all frequencies. In the case of relative perturbations and integral Lipschitz filters, the stability versus discriminability trade-off is different at different frequencies. There is an advantage on getting your high frequency components and somehow moving them down into low frequencies. Now, if you have studied signal processing in the past, you know how to move high frequency components into low frequencies. That's a demodulator, but a demodulator in the context of neural networks is called a pointwise nonlinearity. So that's the property, or that's the conclusion we are after. The relative perturbations give you a stability trade-off that depends on the frequency. There is therefore value on getting your high frequency components and move them into low frequencies. Now, this latter explanation that I gave is much more lengthy and more difficult to explain than the one I use as a shorthand, okay, which is that the Lipschitz filter cannot discriminate high frequency components. When I say that, you know that mathematically what I mean is that the discriminability versus stability trade-off with respect to relative permutations requires the use of integral Lipschitz filters, and that trade-off depends on the frequency of your features. I'm going to talk a little more about these stability trade-offs, but before I do that, okay, I need to tell you about the stability properties of graph neural networks, because both of these theorems, they apply to filters. They do not apply to graph neural networks. But it's not difficult to see that GNNs will inherit the stability properties of the filters, by which I mean that if you use Lipschitz filters and additive deformations, GNNs with Lipschitz layers are going to inherit the stability of the filters to additive deformations. If you consider integral Lipschitz filters and relative deformations, GNNs with integral Lipschitz layers are going to inherit the stability with respect to relative deformations of the shift operator. Mathematically, the theorems that I have to introduce require that I introduce some normalizations, which I am introducing simply to avoid the appearance of constants that wouldn't have any meaning. I am going to assume that my filters have been normalized so that they have unit operator norm. And I'm going to assume that the nonlinearity is Lipschitz and normalized, so that sigma of x2 minus sigma of x1 is less than x2 minus x1. And if this is easy to achieve with the scaling, by the way, but it's true of ReLUs, hyperbolic tangents, and absolute values. And if you join both assumptions, it's easy to see, by the way, also that the input energy is that if the input energy is bounded, then all layers are going to have energies that are bounded by 1 as well. In any event, the two important assumptions here are these. So the filters are normalized and the nonlinearities are normalized, okay? If we add this hypothesis to the three that we had before, so I am now looking at a GNN. This GNN is running on two different filters, S and S hat. These filters are related by an additive perturbation model. The error matrix has norm epsilon, eigenvector misalignment delta. The layers are capital L of them, and all of them are Lipschitz with constant C. If the filters have unit operator norm and the nonlinearity is normalized Lipschitz, as I have stated before, then the operator distance modulo permutation between the output of the GNNs is bounded by this quantity, which is the same quantity that we had before, propagated over L layers. So it is essentially the same bound, okay? And the easy way to remember this statement is to say that a GNN in which layers are made up of Lipschitz filters inherits the stability of the Lipschitz filter. And actually, if you go through the proof of this statement, you will see why I use the word inherit, because really the proof is not complicated. It's just noticing that the nonlinearity is pointwise and that therefore graph deformations have no effect on the action of the nonlinearity. Now, this theorem is not the interesting one because I already told you that additive perturbations are not the most interesting ones. The perturbations that are more interesting are the relative ones. In this case, we need to change hypothesis number 3 and hypothesis number 1. The perturbation has to be relative. The layers have to be integral Lipschitz, but we keep hypothesis number 2 and we keep hypothesis number 4. The error matrix has norm epsilon, eigenvector misalignment constant delta. The nonlinearity is still normalized Lipschitz. The filters have unit operator norms. If all of these conditions are satisfied, the operator distance modulo permutation between the GNN run on filter S and the GNN run on filter S hat is bounded by this quantity, which again is essentially the same bound we had for the case of integral Lipschitz filters. It's just that the bound is now propagated over a total of capital L layers. Therefore, a GNN in which the layers are integral Lipschitz inherits the stability of integral Lipschitz filters. And it does so because the nonlinearity is pointwise and graph deformations have no effect on instruction. Now that concludes the theorem part of the talk, but let me elaborate a little more on the meaning of these theorems, okay? The theorems that I have proven are 4, but 2 of them are there just for comparison purposes. The 2 theorems that are relevant are the following 2. The first theorem says that if I have relative perturbations and a Lipschitz and an integral Lipschitz filter, the integral Lipschitz filter is stable to these deformations. The second theorem says that if I have a GNN made up of integral Lipschitz layers, the GNN is stable to relative deformations of the graph. Let me repeat that to make sure it's clear. We have integral Lipschitz filters being stable to relative deformations of the graph. And we have GNNs made up of integral Lipschitz layers being stable to relative deformations of the graph. It is easy to see why these theorems hold true. And in order to see why these theorems hold true, let's go back to the frequency response of a graph filter, which I had introduced at the end of this morning's talk. We have these filters, but we know that the filters are completely characterized by the frequency response. What is the role of the filter? The role of the filter is to instantiate a specific set of eigenvalues. The blue shift operator here instantiates the set of blue eigenvalues. The green filter instantiates a different set of eigenvalues, the green eigenvalues that I'm showing here. The meaningful perturbations that we studied are relative. They are of this form, but conceptually, we can learn all there is to be learned if we just study dilations, in which I get the graph shift operator S, and I scale it by 1 plus epsilon, meaning my error perturbation, my error matrix is epsilon times identity. Epsilon times identity over 2, to be more specific, but anyway, so I'm just scaling the shift operator. What happens when I scale the shift operator or when I dilate the shift operator? Well, the eigenvalues, they get dilated as well, okay? Therefore, the frequency response gets instantiated on dilated eigenvalues. For frequencies, for features that live in low frequencies, there's not much of a change. For frequencies, for features that live in intermediate frequencies, there is a little bit more of a change. And for features that live in high frequencies, there is quite a lot of a change. Right? So higher eigenvalues move more. Signals with high frequency components are more difficult to process accordingly. Why? Well, because even small perturbations of the graph are going to yield large difference in the filter values that are instantiated. Right? So for example, here at high frequencies, we think that we instantiate h of lambda I, but in reality, we are instantiating h of lambda I hat, the dilated eigenvalue. How do we avoid the problem? Well, we avoid the problem with an integral Lipschitz filter, in which, lambda times h prime of lambda is bounded by C. Why do we solve the stability by using an integral Lipschitz filter? Well, because either the eigenvalue doesn't change because we are looking at low frequencies, right? So lambda I here, lambda low here, and lambda hat low are very close to each other. Or if we are looking at high frequencies, the eigenvalue moves a lot, but the filter doesn't move. By the way, that's the proof of the stability theorem. It's these observations and 3 pages that allow you to make this observation. But this is the observation you need to make to prove the stability theorems that I presented you. That if you're using an integral Lipschitz filter at low frequencies, the filter doesn't move. The eigenvalue doesn't move. At high frequencies, the filter doesn't move. Therefore, none of the eigenvalues really moves. Therefore, the filter itself doesn't move much. But anyway, so I could call this the proof of the theorem for the particular case of dilations. And actually, if I consider dilations, this is how I would prove the theorem. I would just make this observation. At low frequencies, the eigenvalues don't move. At high frequencies, the filter doesn't move. But anyway, so, pictures are worth 1,000 theorems, but only when we have theorems. But we have proven the stability theorem. So, it's not like I'm talking in the air here. So this can be substantiated mathematically, okay? Now, but what is this? What is this telling us about the stability versus discriminability trade-off of graph filters? Well, it tells us that there is no trade-off actually. Why? Well, because suppose that you're trying to discriminate features that live in low frequencies. So, you think you're instantiating h of lambda L, you instantiate something close. So, you have trained your filter, you now have perturbations, your filter still works well. Now, at intermediate frequencies, things start to fall apart, but not by much, right? However, as you keep increasing the frequencies, you're going to reach the point where you have your beautiful filter designed to capture your feature lambda h. But when the graph is perturbed, the filter actually instantiates lambda hat h, which is far apart, far away. I mean, it doesn't really capture any of the energy of the feature that you were trying to capture. Therefore, it is impossible to discriminate high frequency components with a stable filter. So you can have a filter that is discriminative or a filter that is stable, but you cannot have one that is both. What I mean more precisely is the following. I mean, suppose that you're trying to discriminate features lambda I and lambda j. I mean, and you do it, you have trained your filter to do that. So this is the filter that learns to discriminate lambda I. This is the filter that learns to discriminate lambda j. You train your filters today, right? So tomorrow you execute in a filter that is a small perturbation. What's going to happen? Well, the filter that you beautifully learn to discriminate the eigenvector Vi is now capturing a very small amount of energy. And the filter that you had beautifully trained to capture feature Vj is now capturing very little energy because of the deformation. Now, I think that it is fair to say, right, that this is not what we would have expected a priori. I mean, it is reasonable to expect discriminability to be in conflict with the stability, but this is not what happens, right? So they are plainly incompatible. There is some trade-off, okay, because increasing C does improve discriminability, but the effect is marginal at high frequencies. And more formally, given a stable filter, there's always a graph with features that can be discriminated by the filter. Now, do GNNs solve this problem? Well, actually, yes, they do, right? Because we have seen that the GNN inherits the stability of the graph filters. That's good, right? So if the filter is stable, the GNN will be stable. But the GNN doesn't have to inherit the bad discriminability properties of the graph filter. We want it to inherit the good stability of the filter, but we don't want it to inherit the bad discriminability. And it doesn't have to, because the nonlinearities are going to demodulate your high frequencies so that stable discrimination is possible in deeper layers. So for example, here I am utilizing these integral Lipschitz filters, which doesn't really discriminate between lambda I and lambda j. I mean, it does isolate lambda I and lambda j from all of the other features that could be present in the system, okay? Now, once I perturb the filter, I am still capturing lambda I and lambda j. I mean, things are not perfect. So something, some things from lower frequencies crept up into my filter. But anyways, so I am roughly isolating lambda I and lambda j. Now, I am not discriminating them, however. But once you process them with a pointwise nonlinearity, this is a real experiment, by the way. So it's a toy experiment, but a real experiment. This is how the ReLU output of Vi is going to look like in the frequency domain. So this is eigenvector Vi. I compute the ReLU of Vi. I reproject into the spectral domain. This is eigenvector Vj. I take the ReLU of Vj and I project again into the eigenvector domain. And what happens is that now I have a lot of garbage in low frequencies, but nevertheless, right, this garbage is stable. So I can separate it with a filter that is both discriminative and stable. So I think that that's the important message that I wanted to convey today, which is this fact. A GNN can be discriminative and it can be stable. Stability and discriminability are compatible. And the reason why they are compatible is because nonlinearities are low-pass operations, which are demodulating high frequencies into low frequencies, where a deeper layer can discriminate them with a stable filter. Now, this is all I had to say. I think I have 4 minutes left, so let me just close with a couple comments here. So graph filters and GNNs enable scalable machine learning on graphs. Graph filters and GNNs outperform fully connected neural networks, and that's, I think, largely explained by their permutation equivariance, which allows the exploitation of internal symmetries. And GNNs outperform graph filters, and I think that this is largely explained by a better stability versus discriminability trade-off. These two are empirical observations. I mean, you can verify this on your own very easily. Graph filters and GNNs, they do better than fully connected neural networks. And I think that the explanation of that is their permutation equivalence. GNNs, they outperform graph filters, and I think the explanation of that is a better stability versus discriminability trade-off. These are uncontestable empirical observations. These are the theorems that I prove, which, you know, there's a distance between proving a theorem and making a practical claim. But anyway, so that's the reason why we prove these theorems, to try and make these practical claims. I owe you a lot of reference. I haven't told you about the beautiful literature on graph neural networks, of which I am responsible for a small, tiny fraction. This is a good survey where you can find a lot of good papers to read. This is a survey on theoretical foundations on GNNs. This is mostly a survey of our work on graph neural networks. You can find it here. If you want to read the paper on stability properties of graph neural networks, it's here. We have also investigated transferability of GNNs. You can find this here. And if you are familiar with the work of Stéphane Malat on stability properties of CNNs, you might have been wondering whether I am ripping it off. The answer is I am ripping it off. I am simply generalizing results that we know hold for CNNs into GNNs. And actually, all of this can be written in a common algebraic language. You can check this paper to read about that. And of course, something very important is that if you want to reach me, you can send me an email. Something even more important is that I have not acknowledged my collaborators explicitly. So please visit my website and look them up. And if you want a better version of this talk, visit this website. That's a course on graph neural networks that is currently running at Penn. And for the most part, lectures, video lectures are available. That's all I had to say. Thanks for listening. And I apologize if I have taken more time than I should have. Thank you.
So I think there were some questions there. There was one from Soledad.
Yeah, is there any intuition on how the filter that captures? So like the question that Soledad is asking is if there is any intuition on how the filter that captures the Chase eigenvector would look like. So that depends on how you want to design your filter, Soledad. So, you know, filters should not be designed, filters should be learned. So that's why that's the luck that you have for being younger than us, right? So we, like people like Rene and I, we had to design our filters in the early 2000s. Now you don't have to design them, you just learn them. It's easier and better. But the filters that I'm drawing here, they are Gaussian filters, right? So you can take the expansion of a Gaussian filter that will give you the coefficients that you need to run. That's it. No? By expansion here, I mean the Taylor's expansion, right? So it's a Gaussian filter. You run the Taylor's expansion of the filter. Those are the coefficients that you will require to implement this as a polynomial on the shift operator. So the other questions are about the availability of slides. And I see that Rene has already posted his, and I suppose that we can post the slides to the workshop's website as well.
Hi, if there's no other questions, I may ask a few more questions.
Yeah. Yes.
So there is the intuition that if the graph is regular, it's hard to find the like other eigenvectors. Is that true?
What do you mean find other eigenvectors?
Like, okay, if your graph is regular, then the constant eigenvector is the first eigenvector. And then, if you want to find the second eigenvector, I think that there is a computational issue with these filters that don't find it. Yeah. Is that correct?
Right. Yeah, it could be. But so there are computational issues with eigenvectors always, right? Particularly if you're trying to compute eigenvectors that are associated with large lambdas. The point is that I'm never computing any eigenvector here. I'm simply looking at the eigenvectors as a way to perform the analysis. All of the operations here are in the nodal domain. What this is saying is that these operations that you're performing in the nodal domain, they are equivalent to doing pointwise operations in the spectral domain. I think that's the important point for me to convey. And the reason why we like pointwise operations is because they are very, very easy to understand and very easy to analyze also. Some other questions that are related to this is, for example, I mean, how do I know what the value of delta is, right? I am comparing modulo permutation. How do I compute the distance between two graphs? I'm not interested in that, right? I'm simply saying, if the graphs are close, then I can derive these bounds.
Do you know if there is like some families of graphs where it's known that these filters are harder to learn than other families of graphs?
I don't know that. I have not studied the learning process at all, right? So that the one that could have more insights about learning is René, who has studied training, but we never studied the training problem. We're just trying to understand what is possible with the architecture and what is not possible with the specific choices of architectures. Yeah, but I would imagine that there are families of graphs where you can say things about stability as well, right? So the idea here has been on purpose to keep the analysis as general as possible. But if you start looking at the specific families of graphs, I mean, tighter results should be possible. No?
Yeah. Yes, thank you.
Well, it's late, and I think that this should be all for today. Thank you all. I had a message from René that he had to leave on the hour. So thank you all for being here on behalf of myself, the speakers and the organizers. It's been a pleasure to have you around, and I hope to see you all tomorrow. Enjoy the rest of your day.